Hello, my friends. Let's look at our Beer's Law worksheet. Whoa, that got really big. And key it out. Identify the variables in the equation below. From your notes, A. Ooh, I'm a little too sparkly for myself right here. Let's go here. A is absorbance, which is unitless. This is often shown as A. This is B, which is path length, which is usually in centimeters, but it could be anything. Oops, I forgot to say equals A equals molar absorptivity constant. Molar absorptivity. It's absorptivity, not absorptivity. Oh. There's a P there. It won't let me do it. Constant. And then C is concentration, most frequently in molarity. So that means I actually don't know off the top of my head the units for molar absorptivity constant, but since this is unitless, B is centimeters and C is molarity, that means the units are 1 centimeter molarity, or centimeter to the -1 molarity to the -1. Let's keep on trucking. Answer the following questions about creating a Beer Law Lambert split. What is a cuvette? It is a test tube. Why do you need to create a blank? The cuvette and water absorb some light, and that needs to be taken care of, to be considered. That means basically you zero it out. How do you select a wavelength to measure a colored solution? Choose the, oh my goodness, I'm not responding. Choose the wavelength of maximum absorbance. So most often you have something that looks like this, and you would pick right here. This is wavelength, and this is absorbance. How would you create a standard curve in a Beer's Law plot? So my standard curve in a Beer's Law plot would be vary molarities. So that means I would do like 0.1, 0.2, 0.3, 0.4. And then I would take the readings of it and then graph the absorbance. So let me put that together. Vary molarities, record absorbance. And then what happens is the next thing that you're going to do is you say, okay, I'm going to take my unknown, and it's right there, and I go, oh, it's 0.3, and that's it. Diagram 1 shows the absorbance of pure acetone, a common solvent. This is sad. I've never seen this before. Diagram 2 is the absorbance of a solution of a solute dissolved in acetone. Solvent of a solution dissolved in acetone. Good. Using diagram 1, explain what's important to make a blank of acetone in this experiment. It tells us not to use 190 nanometers because that's where the height is, right? So see this guy right here, this guy right here, those are false heights, false peaks. Whoops, I put nanometers. All right. When the student creates diagram 2, she finds that the absorbance at 280 is slightly more than it should be. What is one mistake that caused the wavelength to be greater than it should? Fingerprints. Oh, I'm going to sneeze. Told you. Fingerprints. on cuvette scatter light and falsely increase absorbance. Determine if the errors below would increase, decrease, or have no effect on the measured absorbance while creating a standard curve of Beer-Lambert. Explain your reasoning. So I'm going to write A equals. There's some distilled water left in the cuvette when the sample is poured into it. So that means concentration would go down. So if concentration goes down, absorbance would go down. Algebraically, abs down when C is down. Just load algebraically, I do. The cuvette isn't properly wiped before placing the spectrometer. So what that means is the absorbance goes up because light is blocked by filth. That's what we're supposed to wipe off, is filth. The molarity of the solution is recorded incorrectly. Can't tell. And that is just the stupidest thing. Are you recording incorrectly? Yeah. Just get out of here. I don't want you in my lab group. Student uses visible spectrophotometry to determine the concentration of COCl2 in a sample solution. First, student prepares a set of COCl2 solutions of known concentration. Then, the student uses a spectrophotometer to determine the absorbance of each of the standard solutions at a wavelength of 510 nanometers. Conducts a standard curve. There we go. Finally, the student determines the absorbance of the sample of the unknown concentration. The absorbance at 0.05 is lower than it should be. Is the solution more concentrated or less concentrated than it should be at this point? It would be, in this case, this is the concentration. Is the solution more concentrated? It is less concentrated because it should be up, at this spot right here, assuming this is right. That means the solution is more concentrated than it should be. It is more concentrated because 0.20 molar, 20 abs indicates 0.38 molar. What could cause this error? Explain your reasoning. Let's see here. What could have caused that error? Why would I have something be more concentrated? Or that could be. So why would that get a reading that is lower than it should be? Didn't dry out. Didn't dry cuvette. So increased molarity from prior trial. We'll take a break right there.